All right. Lovely to see everybody again. Welcome to Lecture 6. So, the aim for today, as we've talked about already, is we've kind of mastered the grammar and the syntax for first order logic, our second formal language. What we haven't done yet is figured out when FOL sentences are true and false. So something kind of parallel to what we did in Lecture 3, where we developed this truth table machinery, right? But remember, the truth tables, that was how we did it for TFL sentences. And unfortunately, we can't use that beautiful, beautiful, beautiful piece of machinery for FOL. And that's because we don't have the same basic unit anymore, right? We've replaced atomic sentences with these predicate term combinations. So we're going to have to do something else. And that's what we're going to talk about today. Now, they're called interpretations. They're often also called basically building models. So that's what we're going to try and talk about. Specifically, I want to super quickly, like just 5 minutes, go back over the stuff about sentences in FOL, in part because highlighting something there is going to help us talk about how to construct interpretations and what they're doing. Then we'll spend a long time talking about the nature of interpretations, basically what they are, how they work, really what they're after. And once we've got a grip on those, we'll be able to use them to talk about truth in FOL, and then further define up a bunch of semantic notions. So basically, remember all the semantic notions we talked about with TFL? Right? So we had things like tautological equivalence, being a tautology, being a contradiction, things like this. Those were all defined in terms of valuations. Well, we can't use those here because we don't have valuations. So we're going to have to come up with different but similar concepts, and we'll define them in terms of interpretations. So that's going to be the last part. That's the kind of big plan. Now again, the opening bit here, just the quick and dirty review, is to make sure that we've got a grip on this sort of fundamental concept of what it is to build sentences in FOL. So that's the plan. With regards to structure today, I thought just because we're going to have to cover a lot of stuff and it can get pretty hard pretty quick, thought we'd go for a bit and then break and then come back. Is that okay with everybody? Okay. And you know, right, if you got to run to catch the train or whatever, because I know it sucks to have a class that ends at 6:30 in the afternoon. It's okay. It's recorded. It's fine. Cool. So let's jump straight to sentences of FOL. So as we remember, FOL as a language is composed of 6 types of symbols. We've got the 2 different types of terms. We have our predicates. We have the connectives, the 5 connectives we inherited from TFL, our brackets that do the same things, and our 2 quantifiers. Now the important thing is our base unit is going to be a predicate and a term. And if it's a predicate and a name, cool, we're done. We've got a sentence. But if it's a predicate and a variable, we've got to do some more work. But that's the basic thought. Our new fundamental unit, I say new, we've been talking about this for 3 fucking weeks, right? It ain't new anymore, right? Our base unit is predicate and term. Now we can talk about, when we're thinking of FOL sentences, a kind of intermediate thing, right? We can't go straight from formula to sentence, or sorry, I should say expression to sentence. We have this intermediate thing that is a formula. And a formula is going to be a kind of proto-sentence. Very simply, it's, right, an atomic formula is an n-place predicate with n number of terms. So if it's a 1-place predicate, is a spy, right? Then it's that is a spy predicate plus a term. Bang, you've got an atomic formula. Could be even an atomic sentence. It's an atomic sentence if it's a predicate and a name. Right? So if it says Igmar is a spy, so S-I, for example, in the examples we've used a few times in the tutorials. That's an atomic formula, but it's also a full-fledged sentence. In contrast, if you have SX, right, where X is a variable, we haven't quite got a sentence yet, but we still have something like an atomic unit. To get a sentence, what we need to do is add some quantifiers. And of course, we have the same kind of construction rules that we had from TFL. None of this should be really surprising. You can put conjunctions, disjunctions, conditionals, biconditionals in the middle. You can slap negations in front. All of this works the same just once you already have atomic formula. The important thing here is, again, clauses 7 and 8. It's the same things we talked about last week, so don't stress too much. 7 and 8 tell us if you have an atomic formula featuring a variable and it isn't already attached to a quantifier, then you can slap a quantifier with that variable in front. So if you have fx, then you can add universal x in front or existential x in front. And only once you've done that does the thing you have graduate up from being a mere formula into a genuine sentence. Because the key difference here has to do with variables. So we have two kinds of variables, if you like. Bound ones, which are connected to quantifiers, and free ones, which are not. A sentence of FOL is any formula, so that kind of intermediate step, that contains no free variables. That is, it's only got names, or if it has variables, they're all hooked up with relevant quantifiers. What this is basically doing, this kind of definition at the bottom here, is saying, hey, for every variable, you know the associated function about replacement. Is it telling you that there's at least one thing you can plug in place of the variable? Or is it telling you that everything can be plugged in for that variable? Again, nothing super wild and crazy. We talked about this last week. But it highlights something. There's basically going to be three types of FOL sentences. There's an FOL sentence that just has a simple predicate and name and doesn't have any connectives at all. There's going to be FOL sentences that just feature predicates, names, and then the main operator is going to be one of our connectives, and, or, the conditional, the biconditional, or the negation. And then the last type is there's going to be FOL sentences whose main operator is one of our quantifiers, either the universal or the existential. So if we're going to think about when FOL sentences are true or false, we're going to have to think about those three different groups. And before we go on with that, we should pause, ask, is it clear about why we get those three groups? So again, we're always going to have predicate and term, and the simplest kind of sentence, the easiest one that we're going to figure out how to make true or false, is going to be when you just have a predicate and a name. Or if it's a two-place predicate, then a predicate and two names. That's going to be our first type. And things just kind of get more complicated building from there. Okay. See, if there are questions, feel free to ask. So let's talk about how we're going to make these things true or false. And the core idea here is going to be this notion of interpretations. Again, you can also call them models. I'll probably slide back and forth between calling them interpretations and models. So, the core idea here. FOL sentences are split up into predicates, terms, and quantifiers. The rest is just sort of stuff to get us to link those other parts. The key thing here, the main gain for moving to FOL from TFL, was that we can start to consider what's true or false about particular objects, if we use names, or some or all of the objects in a relevant domain. Nobody here is over 3 meters tall. That's a claim about the people in this room. And that's not really an easy claim to express using TFL, but we can do it with this language because we have a tool to let us say it's not the case that anyone. Okay, so that's the cool kind of neat thing that this language does. It gives us predicates that we can then ascribe or not ascribe to objects in the domain. When we interpret FOL sentences, the kind of core thought here, when we interpret FOL sentences, decide whether they're true or false, what we're going to do is decide whether predicates apply or don't apply to objects in the domain. This is really what interpretations are. They are going to tell us, hey, of the things that are in your domain, these ones are the ones that fit this predicate, and these ones don't. And by doing that, it's going to then allow us to do the same things we did with TFL and the truth tables. The connectives are going to function like they did before. But instead of just doing evaluation and assigning truth or falsity to atoms, we have to see, hey, are the objects picked out in the extension of a predicate? Do they satisfy the predicate or not? If they do, then the predication's true. If they don't, the predication's false. So to give it a term, I already used it, we can say that the collection of objects that satisfy a predicate are the predicate's extension. It's literally the things out in the world that satisfy the property. Now you'll sometimes hear FOL being described as an extensional language. And that's because really what it's concerned with is basically sets of objects. Something we're going to talk about right after the midterm, a couple weeks. But again, the core idea here is that what's really going to drive sentences being true or false is what objects in the domain are in the extensions of predicates and which ones aren't. So, how do we figure out the extensions of predicates? Because that's going to be the driver. Well, there's actually two ways we can do it. When we're building interpretations, because let's be clear, interpretations are under our control. We can do them indirectly, so we can fix the extension of our predicate indirectly. And we do this by saying, hey, our predicate letter stands for some property out in the world. And then what we need to do is go find the things in our domain that actually have that property. So if we say, hey, the predicate D stands for a dog that lives with Nathan. Then to find out the extension of the predicate, you've got to go look and see what are the dogs that live with Nathan. In this case, it would just be my dog, Mira. But note, to do that, you actually have to go out and look. When you indirectly stipulate the extension of a predicate, you specify a property, and then you have to find out what things do or do not have that property. Let's take the domain of the numbers, all the countable numbers. Cool. Let's have the predicate, I don't know, P be is prime. What's the extension of being is prime? Well, crap. We've got a hell of a lot of work to do before we figure that out. Probably an infinite amount of work. So again, indirect stipulation, you specify a property, and then you go and see what objects in the domain do or do not have the property. That's too hard. I'm fucking lazy. I don't know about you guys. I don't like getting out of my armchair. So instead of indirect stipulation, what we can do instead is directly stipulate. When we directly stipulate an extension, we just give a list. And the list we give are the objects from the domain that we are going to say satisfy the property. So in this case, if we wanted to describe the extension of D, just list the things Mira, and that's it. So the key difference here, indirect stipulation, you specify a property, then go discover what things in your domain satisfy it. Have that property. Direct stipulation, you just give me the list of things that you want in the extension. Now here's the really rude trick. So far, when we've been dealing with FOL, we've played it as if the predicates we've been using stand for real properties out in the world. Being a spy, being vegetarian, being a dog that lives with Nathan. But that's just so that we could understand the language. When we really get down to brass tacks, predicates in FOL stand for whatever the hell we want them to. We don't care. And importantly, extensions of predicates are arbitrary. We make interpretations. And because we are making interpretations, we can make the extensions of the predicates any damn thing we want. This is important because it stresses again that there's a deep sense that formal logic doesn't really care about what things go together in any kind of natural way. Formal logic doesn't care. It's genuinely egalitarian. Any way of carving up the world is just as good as any other one. What that means is that reading the extension of D as Mira is just as good as reading the extension of predicate D as every person who's in this room. Both of those are perfectly good assigned extensions of any predicate we want. An individual letter doesn't really stand for being a spy or being a vegetarian. It just does on one interpretation. But we can make any interpretation we want. I'm stressing this because it's very important to see, right? Everything we've done has been trying to kind of get us to understand the language, and now we're going to cast a lot of it aside. Once you've used the ladder, we kick it away. That's effectively what we're going to do now. So, to give you an example, suppose we're talking about the universal domain, right? And let's introduce the predicate Z or Z if you're feeling particularly kind of Anglo, right? So, Z is true of all and only the following. Me, the Eiffel Tower, and anyone who's ever lived in Tilburg. Is this a terribly natural property or predicate? No, but who cares? It's perfectly good for our formal logic purposes. And then we can just add some names to the mix, right? So we'll have little n for Nathan and little d for Darth Vader, right? So again, I've introduced you to a predicate. I've fixed this extension directly. I stipulated it. So thinking about this, right, is Zn true on this interpretation? Yeah, because I'm in the extension of Z that I directly stipulated just a second ago. Is Zd true? No, because Vader, as far as I'm aware, isn't me, he isn't the Eiffel Tower, and he's definitely not somebody who's ever lived in Tilburg. He's not in the extension of the predicate, so his name attached to the predicate gives us a falsity. He's not in the extension. If you understand these two, you're 90% of the way to what we need to do. The other thing to note is that if I said ZX, ZX isn't true or false because you haven't said anything yet. In order to say something, we need to have this attached to some quantifier. So, to go back, looking at this, right? We've got the universal domain, we have this predicate, and we have these names. Is for all x, zx true? Is for all x, zx true? Is universal x, zx going to be true? Is it true that everything in the universe is either me, the Eiffel Tower, or has lived in Tilburg? No. In fact, we can show it's false by just picking anything that's never been one of those things. Let's take Paris, the city. Cool, Paris isn't me, it isn't the Eiffel Tower, and it's certainly never lived in Tilburg. Cool. The universal claim is false. Is there something in the domain that satisfies the predicate Z? Yeah, I mean, there's me, there's the Eiffel Tower, there's any of you who live in Tilburg or have before. But note, ZX by itself doesn't say anything, so it isn't true or false. We have to know what function do we replace the variable with. Is it with everyone? Is it with someone? If you've got that little bit that we just did, you've got it all already. The rest is just going to be getting the details down. So, put really bluntly, one-place predicate descriptions are going to be true if and only if the object denoted is in the extension of the predicate. The rest is just going to be kind of extending that idea. So what do we do with two-place predicates? How do we make sense of loves or is taller than? Well, here we can't just say the object's in the extension, because you need to be in the extension in the relevant place. Finn loves Princess Bubblegum. Princess Bubblegum famously does not love Finn because she loves Marceline the Vampire Queen, as we all know and love. So, how do we make sense of two-place predicates? Well, with these, we have the same tools. We can indirectly stipulate. We go out and we find, hey, what are the relations that hold? We look at Finn, we look at Marceline, we look at Princess Bubblegum, we find who loves who. Or we directly stipulate. But when we directly stipulate, instead of just listing the people who are in the extension, we list the pairs. And we list the pairs in the order. So we could say, right, is friends with. Well, we have the pair Nathan and Mira. So I'm friends with my dog. My wife is friends with my dog. My dog, not friends with us. She hates fucking everybody. Right? But note, what this is driving home is that the order here matters. This is telling us that you can plug me in the one spot and Mira in the two spot. You can plug Amanda in the one spot and Mira in the two spot, but you cannot plug Mira into the one spot with anybody because there's no pair where she's in the first place in the order. So, with one-place predicates, you can just give me a list. With two-place predicates, you've got to give me a list of ordered pairs, telling me who has the one spot and who has the two spot. Now, sometimes it's not really going to matter. Romeo loves Juliet, Juliet loves Romeo. Cool. What that means is that you've got two pair in the extension of loves. You've got the ordered pair Romeo-Juliet, and then the ordered pair Juliet-Romeo. This is just reinforcing the point when we talked about relational predicates that the order we write the terms in matters. The order tells us who's in the one spot and who's in the two spot, whatever the relation is. So far, so good? Okay. So again, what are we really doing? We're fixing the extensions of predicates, and by fixing the extensions of predicates, it then settles the kind of atomic formula, and then it's just going to go gravy from there. One thing to note, identity is a special predicate. Remember when we talked about it last week. Identity is special in two ways. It's special grammatically. It's the only one we write in between the terms. And it's also special in that it is the only predicate where we never ever specify either extension or what it stands for. It's always numerical identity, and we have to work out what's going to be identical to what. We can't kind of stipulate this. There's no messing around with identity, unfortunately. Okay. So, finally then, what's an interpretation? An interpretation is going to be a model. An interpretation consists of three things: a specification of a domain, an assignment of exactly one object within the domain for each name we're considering, and most importantly, for each predicate we're wondering about, a specification of an extension. Note, this is a lot like a symbolization key. It's a lot like a symbolization key. The big difference is this part. Because what we've been doing so far with our symbolization keys is we've been treating predicates basically as being fixed indirectly. S stands for is a spy. V stands for is a vegetarian. T stands for one, trust, two. That doesn't fix the extension unless we go out and look. But what we want to do when we're building interpretations is we want to specify extensions. Because only once we have the extensions of the predicate will we know whether atomic formula are true or false. So it's literally the list of things that satisfy the predicate. Yep. Just the list. Just the list. So you could think about it this way, right? The extension of person in this room is going to be a list of each one of our names. And what it's telling us is that you can take each one of those objects and plug it into the predicate and get a true. And then if we reach out and grab somebody who's not in the room and plug them into the predicate, they're not on the list. So it literally is just a list of things that satisfy a predicate. In contrast, when we think of the extension of a two-place predicate, it's the ordered pair that satisfies. So, big tall man, right? If you take him in the first place and me in the second, you get an is taller than satisfier. If you take me in the first place and him in the second, you don't. Much taller than me. Again, all we have here is just a list of things that satisfy the property or satisfy the predicate. Is that clear? Before we go on and do anything else. Because the rest of it, if that bit don't make sense, then it's all just going to be a mess. Okay? So, again, an interpretation is going to give us a domain. If there's any names, it's going to tell us, hey, what objects in the domain are the names for? And then finally, and most importantly, it's going to tell us what objects in the domain satisfy which predicates. In this way, interpretations fix the extensions of predicates. In turn, these will fix the truth values of the atomic formula, and then that's going to trickle up and give us the truth values of the FOL sentence in general. In this way, we indirectly settle the truth value of FOL sentences by fixing extensions. Fixing extensions gives us the atomic formula, which then is going to give us whatever the more complex ones are. So here's a simple interpretation, right? We've got universal domain. We have some predicates. So I've assigned two predicates. I've ascribed the extensions indirectly. I've just taken predicate D. I'm going to indirectly ascribe its extension by saying, cool, just go find the things in the domain that are dogs. Same thing with predicate F. I've said, go find the things that are friendly. So I haven't given you the list of things. We have to go do some work to see what's actually in the list. But I've also given you two predicates where we've directly given the extension. So here's the list of things that are Z, right? It's the same one that we had before. And here's the list of things that are satisfying predicate A, Darth Vader and Mira. Probably A is something like the property of being full of rage and hate. I don't know, it doesn't matter. When it comes to interpretations, we don't actually care what the predicates stand for. I don't care if predicate A is supposed to pick out the property of being full of hate. It doesn't fucking matter. What matters is the extensions, because that's the only thing that matters for determining truth or falsity. And then I've got some names here. I've got a name for me, a name for Vader, and a name for Mira. Again, note, it looks a lot like a symbolization key. But the difference here is that what we're doing with these is we're specifying an extension. Specifying which things in the domain do or do not satisfy the predicate. Notably, you can also build these sorts of things with diagrammatic models. So you can draw some nodes. You've got 1, 2, 3, 4 nodes. And then we can just draw arrows to represent relations holding. So this arrow here means that whatever relation, we'll call it R, holds between C and A. So RCA is true on this interpretation, because there's an arrow that starts at C and ends in A. But on this, is RAC true? On this diagrammatic interpretation, is RAC true? No, right? There's no arrow that starts at A and points at C. So this is just another way to do the same thing. You could do this with a list. That's fine. I don't mind. But note, diagrammatic interpretations are very easy if you're only dealing with two-place relations. Draw an arrow when it holds. Don't draw the arrow when it doesn't. Bang. You get something like this. We'll talk more about these in the tutorial. But note, this is the kind of thing that really only works if you're only dealing with two-place relations. If you're dealing with one-place predicates and relations, it gets a bit messy. Okay. So that's the core of what an interpretation is. Now we can use these. And we can use these to define up a notion of truth. And it's going to be very straightforward. It's just going to be, hey, a sentence is true in an interpretation if, well, the predications are true and the relevant connectives work the way that you think they do. But let's go through them one by one. So remember, up at the top, I said there's broadly three kinds of FOL sentences. There's atomic ones, which is just going to be predicate and names. There's sentences whose main operators are connectives. So negation, conjunction, disjunction, conditional, biconditional. The same ones we dealt with before. And the trickiest one, sentences whose main operators are quantifiers. In order to make sense of truth for FOL, we're going to have to think about each type of sentence. The first two are going to be really easy. Let's talk through those before we go for our break, okay? So, how are atomic sentences going to be true? Here's the fancy way to say it. We'll give you a slightly less fancy way in a second. When R is an n-place predicate, and A1 through AN are names, then R A1 through AN is true in an interpretation, if and only if R is true of the objects named by A1 through AN in that interpretation, in that order. What's the fancy way of saying it? Cool. That's just a nice way to say, right, if you've got, say, ZM or ZN, if you remember, right, Z was that predicate we defined a few slides ago, which was the extension of me, the Eiffel Tower, anyone who's ever lived in Tilburg. Zn is true in an interpretation if N, the thing named by N, is in the extension of the predicate Z. It's false if the thing named isn't. We did this already. Remember when I asked you about whether Zn is true or false earlier. You said yeah. And Zd, where D was Vader, right? Was that true? No, because he's not in the extension. That's it. That's the simplest thing. An atomic sentence is going to be true if the things named are in the extension, and it's false if they're not. The other thing to note is that an identity claim is going to be true in an interpretation if and only if the two terms, the two names, name the same object. Clark is Superman. Cool, if it turns out that those are names for the same object. Bruce is Superman. That's going to be false if it turns out Bruce names this thing and Superman names this thing. Nothing really surprising here. If on a given interpretation, the names are names for different things, then they're different things. The identity claim is false. Okay, so there's our easiest one, atomic sentences. An atomic sentence is true in an interpretation if the thing named is in the extension of the predicate that we picked out. Bingo. The rest is gravy. So we can also use our diagrammatic interpretation to kind of represent this, right? Take our diagrammatic interpretation. Let's take RDA. Is RDA true on this interpretation? Right? There's an arrow going from D to A. Bang. Is RBA true on this interpretation? RBA. True or false? What do we think? It's false, right? There's no arrow going from B to A. Again, you can literally see it. Got this, we're good. Same thing too. We talked about this just a second ago. If we're using the interpretation we talked about earlier, Zn, true on this interpretation, because the thing named by n is in the extension. Zd is false on this interpretation, because the thing named by d here isn't in the extension. Notably, what these sentences express, what they say, depend on what interpretation we're using. So there's going to be plenty of interpretations where Zn is false. Let's have N here stand for, I don't know, the city of New York. That's a variant interpretation, and on that different interpretation, this would be false. So truth or falsity is always relative to a model, relative to a particular interpretation. Okay, so there's our atomic sentences. What about our second type? How do we do with the connectives? Well, I've given you the slightly scary red box, but the shorthand for the red box is the connectives work just like they did before. For the negation, if the thing it's negating is false, then the negation's true. For the conjunction's true if both conjuncts are true. The disjunction's going to be true if at least one disjunct is true. They work exactly like they did before. They work exactly like they did before. So nothing new here. So the atomic sentences are easy. Look to see, are the things named in the extensions of the predicates we're looking at? The connectives are easy. They work exactly like they did with TFL. Now, we haven't talked about the quantifiers yet, but if we can do this bit, we've got about 50% of what we need. So how are we feeling with these ones? Does it make sense so far? Let's find out. So, here's a sample interpretation. I had this last year. Students told me they don't know The Simpsons really anymore, but people know The Simpsons at least enough, right? Like, if I talk about all the Simpsons characters, you've got at least a broad grip on who I'm talking about? No? It'll be good enough for government work. So let's have our domain be all the Simpsons characters. We'll have the predicate A, B, and O be fixed indirectly. Right? So we have the A is American, B is a baby, and O is a relational is older than. And then we'll have two names, one for Maggie and one for Homer. So note, in this case, I've indirectly fixed the extensions of these predicates, but that's just because it's a little bit easier for this example. We could have done this directly, just it would be a horrifically long list, or at least this one and for this one. So, on this interpretation, is our first sentence here true or false? Is this claim true or false? Well, let's think, right? So the main operator here is the negation. So the negation is going to be true if the sentence it's negating is false. And the way we assess the negated sentence is we go and think about, is the ordered pair M, H in the extension? Is Maggie older than Homer? No, right? Maggie's a baby. Homer's her father, right? So clearly the negated sentence is false. But if the negated sentence is false, what's the truth value for the negation? It's true, right? Bango. We've already got the first one here, right? So our first sentence is true on this interpretation. How about our second sentence? right? So in this case, our main connective is the conjunction. It's going to be true if both conjuncts are true. So we go and look and see, hey, in this conjunct, is the thing named by M in the extension of the predicate be? Maggie is the baby. So cool, first conjunct nailed. And then the other one, we go see, hey, is the ordered pair HM in the extension of O? Is Homer older than Maggie? Yeah. So both conjuncts are true, conjunction's true. So far, so good? Clear how we go? Beautiful. How about our third one? How about our third one? What do we think? True or false on this interpretation? Well, let's think. What's the main connective here? What's the main connective? It's the biconditional, yeah? It's the biconditional, right? And remember, from TFL, our biconditional is true if and only if both sides have the same truth value. So in this case, are both sides of the same truth value? Well, is Maggie older than Homer? Okay? And then the other side says, it's not the case that M is in the extension of A. Or, in the terms that we're talking about here, it's not the case Maggie's American. True or false? It's false. So, both sides false, that means our biconditional is true. Again, I'm going slow here because I want people to sort of see the structure of how we do this, right? The extensions of the predicates fix the truth or falsity of these atoms, and then those in turn fix the truth or falsity of the connectives, exactly like they did with TFL. Exactly like they did with TFL. And for our fourth one, what do we think? What, is our fourth one true or false? Fourth one's true, right? Our fourth one's true. So it's a disjunction. It's true if even one of the disjuncts is true. And here's something very satisfying. Homer is always going to be identical to Homer. So that side's just true. So cool. Easy. We don't even need to care about the other side. And finally, our last one. Is our last sentence here going to be true or false on this interpretation? So what's the main connective of our last sentence? It's the conditional, right? It's a conditional. And is our antecedent true or false? It's false, right? Homer and Maggie are not the same objects in our domain. And what's the truth value of a conditional with a false antecedent? It's always true. Always true. So in this case, we see the antecedent's false, bang, we know that it's true. Do we see it? Do we see it? Again, don't worry too much if it didn't fire right away. What matters is that you see the process for figuring it out, right? We figure out the extensions, that tells us what the various parts are going to be, and then we go back and remember how these things worked from TFL. Yeah. Good. So this is why it's almost always better to have direct stipulation of the extensions of predicates than indirect. Because if it's indirect, we need to know a bunch of stuff about the domain. Right? I need to know who's older than who in the domain. If we don't know, then we're epistemically in a bad space. This is why direct stipulation is so much nicer. Because I could just give you the pairs that satisfy, and the ones that aren't on the list. It's a nice example because it drives home what's valuable about direct stipulation. But of course, if we have a domain that's this big, and there's a crap load of Simpsons characters, right? Listing all of the ones that are American, that's going to be a list of like at least 300 different characters. So sometimes it's easier. For pragmatic purposes, we do indirect. But that puts us in a disadvantage if we don't know much about the domain. So it's a kind of trade-off here. The nice thing, though, is when we're building our own interpretations, which is what we're going to get to, when we construct our own interpretations, always go for the direct option if you can, because it makes things so much clearer. Okay, before we take the break, pause. Are there questions on what we've done so far? Are we feeling okay, at least about these? So we know how to do atomic sentences, right? It's just literally, is the thing named in the extension? And we know how to do the connectives. It works just like it did with TFL. So all we've got to do now is figure out how to deal with the quantifiers. All we've got to do now is deal with the quantifiers. That's what we're going to do when we come back. So it's 36 now. So we'll take a 10-minute break to 46. Is that okay with everybody? Take 10 minutes, and we'll come back and go from there.